Welcome to our monthly Gateway to Translation webinar series, which are organized by the University of Manchester and also the Cambridge Academy of Therapeutic Sciences. My name is Athina Markaki. I'm a professor at the Division of Mechanics, Materials and Design of the Engineering Department in Cambridge. My research focuses on vascularization for the development of tissues at clinically relevant dimensions and also on conduits on tubular scaffolds actually to replace diseased or damaged conduits in the human body. So very much in the field of regenerative medicine. So it's a great pleasure to introduce our speaker today, Dr. Jasper Van Hoorick. Jasper is a Belgian chemist and innovator leading BIO INX. It's a Ghent-based biotech startup specializing in BIO INX for 3D printing. Jasper received his PhD from Ghent University and his master's from University of Brussels, focusing on biodegradable polymers and also lithography for ocular tissue regeneration. Now, his ambition, as you can see from the title, extends to bioprinting functional human tissues and eventually whole organs for regenerative medicine and space research. So very exciting stuff. Now, before we start the talk, I'd like to discuss a few housekeeping rules here. So first of all, that the talk will be recorded. Please, and I can see that almost everyone has done this, please keep your microphone on mute. For the QA session afterwards, you've got the choice either to use the chat function to post any questions, or you could raise your virtual hand. I think the second is probably better in my view. And at the end, you might be asked to complete a short survey. So without any further ado, over to you, Jasper. Thank you very much for agreeing to give a talk.
All right, thank you very much for the introduction. And indeed, I will talk a bit about biofabrication, 3D bioprinting, and the role of materials there. And then, well, before I always introduce biofabrication, I always like to make this comparison with cars, because the fun thing about old cars or cars in general is that you can keep them working if you have the right spare parts. But of course, for humans, the situation is different, because for humans, if you have an injury or a disease, you don't have the right spare parts. I mean, you can argue that you have donor organs, but there's quite some issues with not donor organs, prosthetics. There's quite some issues with prosthetics. They're always going to be foreign to your body. And you also have donor organs, but there's quite some issues with donor organs as well. One thing is that the supply does not meet the demand, and let alone all the issues related to your immune system not being able to support foreign organs. So what if one day we could actually 3D print these tissues? Then it may sound like science fiction, or is it more science? And of course, we're all here. There is quite a lot of science going on there, and I think most people still remember or have heard of this mouse with the ear on its back. But if you look at when this mouse was alive, it's 1996, which is almost 30 years ago, and still the technology is not there. Back then it was world news, and they promised that there was going to be lab-grown organs for everybody, but it didn't happen. And why is that? Well, if you ask me, it's because not the right technologies we're using, and the right technology, in my opinion, is 3D printing. And the concept there is quite easy, actually, the concept in that sense. You have your cells, you put them in a 3D printer, you put a certain image in your 3D printer, 3D design, mimicking the tissue you want to print. You print your cells, and then you put them in tissue culture, and you have your organ, which you can implant. So that's the theory. Of course, practice is a little bit more complicated, because first of all, if you think about 3D printing, and especially if you think about the materials, and the materials which are there are hard plastics, toxic resins, metals, nothing which in any way resembles the human body. And another thing, if you then look at research going on into materials for 3D printing, then we see in a lot of cases that the technologies, there's poor standardization, and the resolution is too low to mimic the right tissue architecture. And this leads to what I call the biofabrication deception. There's a lot of researchers who have a lot of experience on 2D cell culture, 2D models, and then they read some papers, they want to go to 3D. So they buy a bioprinter, they make some materials, or they buy some materials. And then next thing, what typically happens is it doesn't work. Why doesn't it work? Well, there's multiple reasons for that. First of all, actually, only the successes are reported typically in literature. If you have a paper describing some bioprinted tissues or bioprinted cells, you only report on the successes and not the whole route to get there. There's often with materials an issue with reproducibility, and there's often a mismatch between expectations and realities because there are many different 3D printing, many different bioprinting technologies, and people often think that there's one printer, one size fits all, which can do everything, but this is not the case. And if you take, for example, a concrete example of gelatin, Elma, which is one of the most popular materials in the field, which was actually developed 25 years ago in the research group where we spun out from in Ghent University. And if you do literature research, you see that every lab basically does something different. And this is one of the issues with 3D printing or 3D bioprinting, because everybody does something different. It's not reproducible. And this gives a bad reputation of gelatin, saying that it's not reproducible, but actually it can be super reproducible. But things like this add to this biofabrication deception and to the reason why the technology is not or hasn't matured yet beyond the research scale. So in that sense, there's a huge need for standardization. And all these reasons are actually at the origin of why we launched the company BIO INX 3.5 years ago. And today I want to tell a bit more about bioprinting and the role of BIO INX, the materials, not the company, in there on this talk called En route to 3D printed organs. What's the role of BIO INX? So with BIO INX, we have a vision that in 10 years from now, you will be able to go to the clinics to get your first 3D printed tissues. Very important, tissues, not organs yet. So that's the first thing, but you can also use the technology to replace animal testing in drug screening, to personalize drug screening and solve the donor shortage in general over time. Of course, this is not going to happen automatically, because if we want to get there, as I mentioned, there's a need for standardization. So we made it our mission at BIO INX to provide reproducible, standardized materials to make the technology truly turnkey, which is what needed if you want to ever translate this into the real world. So getting back to 3D printing, what do you need if you want to 3D print a tissue? You need to have cells, of course. Cells are the building blocks of any tissue, and you need to have a specific design to know where to put which cells. But of course, cells on their own, they're very difficult to manipulate, very difficult to print. So you need something which makes them printable, which are called the BIO INKs. And then, as I mentioned, the concept is straightforward. You print the cells, you put them in cell culture, and you use it for organ regeneration or to replace animal testing. And this is a field which becomes more and more interesting. Why? Because, first of all, nobody likes animal cruelty. Second of all, there is a ban on animal testing ongoing. In 2013, it was already banned in Europe for cosmetics testing. Since 2021, it's banned in Switzerland, for example, for drug testing. And things are getting more and more strict. Also, we see in the US that FDA is phasing out animal trials. So there's a need for alternatives. And what could be an alternative? Organ on chip. But if you want to have an organ on chip, you need to have this natural complexity, and there bioprinting could step in. So, as the title of the talk already gave away, and the company name as well, what I'm going to focus on today, and what I think is key in making biofabrication work, are the BIO INKs. Because what does a good BIO INK do? A good BIO INK mimics the extracellular matrix, has to keep the cells alive before, during, and after printing on the one hand, and on the other hand, it needs to make the cells printable. Now I write here that printable with multiple technologies because, as with every new technology, there's many different route to Rome, so to say. So there's many different printing technologies, and it's not quite clear which will be the predominant one. And in the next half an hour, I will try to shed a light on the pros and the cons of the different technologies and what I believe they would be the technologies to go for. So we have to mimic the extracellular matrix. And if we look at the properties, then we see that the natural extracellular matrix is highly hydrated. It contains a lot of proteins and polysaccharides. It's mainly based on collagen. It's cell interactive. Cells can remodel it, so it's biodegradable. So these are the properties we aim for from a biological point of view. And from a processing point of view, we need materials which have sufficient mechanical properties. There are some technology-dependent properties which I will get to, but mainly they need to be easy processing, easy processable, and photocurable in a lot of cases. So if we map these different requirements into some keywords, then we can start looking for the ideal bio-ink or the ideal biomaterial. And a great starting point for a biomaterial is looking at nature, collagen, and polysaccharides. What are they? They are polymers. So why not start our bio-ink from a polymer ourselves? I don't think I need to say what a polymer is, but a polymer is basically a sequentiation of different small molecules into a chain, which is a polymer chain. So as I mentioned, the goal is that we want to mimic nature. And if you want to mimic nature, then just start from nature. So one interesting material can be collagen, which is also very popular in cosmetics and food supplements. And what's interesting in collagen, it is a hydrogel, meaning that you can that it can absorb large amounts of water without dissolving, which is typically what the cells like. So if you think about collagen, there's another material which comes to mind, which is derived from collagen, which is gelatin, which we know from the kitchen and from the candies, which has a long track record and actually in a lot of cases can be more attractive than collagen. And then a third typical material, which you again find in the cosmetic field, is hyaluronic acid. If we look at these materials and we add the properties there, we see that all three of them, they are hydrogels, they're biocompatible, they are cell interactive. Collagen and hyaluronic acid are physiologically stable. Gelatin is not because it dissolves at 37 degrees, well, even at 30 degrees. And they are biodegradable, so biologically they are doing quite well, but printing-wise, they are not, because they're very difficult to process, they're not photocurable, and they're far from robust. So we need to find other materials. So what else is available in nature? So there's polysaccharides. So let's look at algae. Another very popular material is alginate, which is a hydrogel of polysaccharide. It's biocompatible. It is physiologically stable. You can process it super easy. It's also used a lot in the kitchen. Downside is it's not cell interactive, it's not biodegradable, and it's still not photocurable and far from robust. So that's nature. Maybe there's other materials we can look into. So let's look at the usual suspects in synthetic ones. Polyethylene glycol is a very popular hydrogel with a large track record in the biomedical field. And polyphenol alcohol are used a lot. Polyphenol alcohol is a material which is used a lot in 3D printing, mainly for sacrificial materials. But again, we see that they're not doing great. So maybe we need to look at other material classes, what's typically used in the field. And polyesters can be also interesting. Why polyesters? Because if you think about 3D printing, they are very popular materials and they are biodegradable and they are biocompatible. Some of them polylactic acid, polycaprolactone, for example. So we already have a whole array of materials where we can start from, but we see that none of them ticks all the boxes. Because what happens with most of them, if you put them into the body, the hydrogels, they would dissolve, they would lose structure. So we need to tackle this chemically. So going from this polymer, we can also go into polymer networks by introducing crosslinks in between them. So we can cross-link these materials, which makes them insoluble. If, for example, look at gelatin, you can transform it into gelma, and then you have a polymer network which can no longer dissolve at body temperature. You can do this via introducing different chemical functionalities. Acrylates, methacrylates are very popular, but you can also use other groups like thiolene or click chemistry or enzymatically linkable groups, because basically you need this network. If we look at these different materials, fortunately there has been quite some literature, and we see that if we methacrylate them or put acrylates on there, already a lot more pluses are appearing, but none of them still fulfills all the requirements. And this is because these are requirements which are very difficult to combine. And this is what's referred to as the bioprinting paradox. Because on one hand, from a biological perspective, you need soft water-based materials. On the printing perspective, you need to have robust, processable, and typically hard materials. And this was also mentioned in a review by Jos Malda from Utrecht, that typically what happens in the traditional biofabrication window is you compromise. So if you look at materials which are very good from a fabrication point of view, they're very bad from a biological point of view. If you have materials from a biological point of view, like Matrigel, for example, they're unprintable. So where do we need to go? We need to go to these novel strategies which have good shape fidelity and good biological performance. And there's many ways to get there. You can do this on a polymer level, so the backbone of your bio ink. You can do this on your formulation level and on your processing level. And I would like to highlight this a bit for the different popular printing technologies. So let's start with the most common one, which is extrusion-based bioprinting or deposition-based 3D printing. This is the one most similar to the commercially available 3D printers, and basically works by depositing your material in a layer by layer fashion, just on top of each other. So what do we have here? Resolution wise, it's the lowest resolution technology. It's hundreds of micrometers. Let's say in practice with hydrogels, 400 to 500 micrometers are about what you can get at. But to get there, your bio ink needs to have specific properties. So I mentioned in the beginning that there's many technology-dependent properties on your bio ink, and here it's mainly the rheological properties, meaning that you need a material which flows very easily during extrusion and keeps its shape very well after deposition. And of course, your material needs to be cell biocompatible. So what are we looking for? A material which behaves like icing on a cake, basically. You can easily extrude it, and it needs to maintain its shape. Unfortunately, if you think about hydrogel, hydrated solutions, most of them behave like shampoo or water. If you extrude them, they will just keep on flowing, and you'll never be able to get a nice 3D structure out of it. Fortunately, we can get this behavior in there by playing around with the formulation. And then we get to materials which we call shear thinning materials, meaning that they have a high viscosity at rest. And if you put mechanical force on them, they become liquid. And once you remove this external mechanical force, they become the viscosity increase again, and they maintain their shape. Typical materials like that are toothpaste or hair gel, for example. And how do you get there? Your active compound in your bioink is always your polymer that will determine your main properties of your material after printing. But in this case, we add a rheological modifier to it. And a rheological modifier is actually a modifier which modifies the rheological behavior. And rheological behavior, rheology is a study of fluid behavior of materials. And by adding some of these rheological modifiers, we can, for example, go from conventional Gelma solution, which is unprintable at 37 degrees, to a nicely extrudable material which has shear thinning properties and keeps its nice filament shape after deposition. Some formulation level. You can also play around on processing level. There have been many different strategies, as also published in a review by Ricardo Levato from Utrecht again in 2020, where you can see that you can play around with a lot of things. You can do chemical cross-linking, as I already mentioned. You can play with physical interactions to get this shear thinning, physical interaction, rheology tuning. It's basically shear thinning. You can have microfluidic or coaxial printing. For example, for alginate, you need a second material with calcium chloride, which you can then deposit together. Or more recently, you can use a support bath. So if we think about chemical crosslinking, I already mentioned introducing metacrylates to gelatin is for example, one of the most popular materials there, which makes the material photocross-linkable. And I already discussed this, so I'll go back into it. But if we look at it from a material point of view, you have your active compound, which is a polymer and a rheological modifier. In this case, you change your active compound into a photopolymer. And of course, if you have a photopolymer, you need to be able to cross-link it, for which you need a photoinitiator, which is a molecule which induces cross-linking upon radiation. And then you can use this cross-linking to have better shape fidelity. For example, you can cross-link it, irradiate it during printing, which is done in the lab of Jason Burdick and was published in Advanced Materials, for which they could get a lot better shape fidelity with materials. In this case, it was hyaluronic acid based. And another strategy is, for example, the use of a support bath. So here you use a granular support bath of hydrogel beads in which you print your structure, and then the support bath supports your material. If you afterwards put it in water or warm water, the support bath dissolves and you can get your complicated 3D printed structure. And with that, even with extrusion, you can already get quite some interesting structures with materials which are basically unprintable if you would do it in a conventional way. And the last thing is you can play around with the polymer. You can, for example, introduce some cues which allows modification after printing. So for example, you can use shape memory materials, which you can deform after printing. And then if you reheat them or put the trigger on there, you can change the shape after printing, leading to 4D bioprinting, where you can have an additional dimension there. This is, in a nutshell, deposition or extrusion-based bioprinting. And what are the downsides of this technology? It has relatively low resolution, 400 to 500 micrometers. If you look at this from a cellular perspective, this is huge. Up until now, there's often reproducibility issues, especially when people are using non-standardized materials. There's a lot of optimization because this rheological tuning can be very tedious. It's a slow technology because every increase in any dimension will have an influence. If you double the size, your printing time goes times 4. So if you want to print large structures, it can take forever, which is again bad for the cells. And because of this low resolution and slow printing, you have limited potential for complexity. But you can actually use it still for materials which don't require too much complexity. For example, a few years ago, there is a in vivo in human study already with collagen-based BIO ink for printing cartilage in Mexico, and also with Closer Read together with University of Leuven have achieved quite some nice results in cartilage regeneration using extrusion-based bioprinting, where we could actually see that the cells, when you differentiate them, increase the mechanical properties of the printed construct with up to 2 orders of magnitude. So thereby showing that you are actually forming functional cartilage. And also you can use, for example, for adipose tissue, or we also in the past have got some quite nice results with it. But what we believe very strongly at BIO INX is that light can be the solution. So also our company slogan is from light to life. And we believe that light-based bioprinting is the future. Why? Because you can go into a lot higher resolution. You can even go in subcellular dimensions. So you could mimic the microcellular environment. That's not the only reason. The other reason is you have high resolution, but also higher reproducibility and scalability, because these materials are these technologies are typically very reproducible, very fast, very scalable. But I will get there in a few minutes. So if we look at the different printing technologies again, let's go into the other extreme. So we started at the low resolution. Let's go immediately in the most high resolution technology, which is two-photon polymerization or multi-photon lithography. So here, how does this technology work? Basically, instead of single photon, you use 2-photon. I will not make it too complicated, but what happens in any photo-induced reaction is you excite your electrons to an excited state, and when they fall back, they release their energy and they do something. In this case, in printing or in cross-linking, upon releasing their energy, they initiate polymerization. And in conventional photo-induced processes, your energy of your light needs to correspond to this energy gap to which you need to excite your electron. But in two-photon polymerization, you basically use light with twice the wavelength. Twice the wavelength means half the energy, meaning that 2 photons or 3 photons, multi-photons, can surpass this energy gap. But of course, this intermediate state doesn't exist. So this means that you can only do this if you have a lot of photons, meaning that you can get simultaneous interaction of 2 photons with 1 photoinitiator molecule, which can only happen if you use high intensity and tightly focused light. And as a consequence, you will only have this in your focal spot, meaning that you will only have polymerization there, whereas in conventional light-based printing, you would have polymerization all along the beam path. So that's the theory, but if you see it in practice, you can see how impressive this is. This is a movie which was recorded at TU Wien in Austria in the research group of Alexander Ovsyannikov, where they actually printed, showed the potential of the technology by printing this small castle here. You can see in this case it's accelerated 10 times, but you can see this is actually recorded through the same microscope objective as the laser is scanned through. So you can see the laser scanning through. The lines are there, and you can see here where we are in the structure. So this is the top view during printing. So you only see the focal plane, and you see we're up into the tower, printing this very fine features. Of course, there's no scale bar here, but in a moment you will see how tremendous the resolution is, because if you look where the castle is printed, castle is actually printed on top of a pencil tip. So you can see that with this technology, you can go to extreme high resolutions, down to microns, tens of microns, and even hundreds of nanometers, which is of course very interesting from a bioprinting perspective. So if we then look at the BIO INK properties there, resolution you can achieve is hundreds of nanometers to micrometers. What's important here, your material needs to be 2-photon active. It needs to cross-link fast because it's very high resolution, meaning it is in a way the fastest printing technology, because your laser can be moved to meters per second or even hundreds of meters per second. But of course, resolution is extremely high, meaning that you need a fast chemical reaction, a fast cross-linking reaction, because if you have this high resolution, if you want to print something bigger, it needs to go fast. I always compare this with trying to paint a wall. If you paint a wall with a large brush, it will go fast, but you lose your resolution. If you want to paint it with a ballpoint pen, for example, you can probably do it, but it will take forever unless you can move the ballpoint really fast. It needs to be cell compatible. Another benefit of this technology is you can do it in the solid or the gel state, because you can scan your focal spot in all 3 dimensions. So if we then look again at the composition, there's an active compound, which is of course a photopolymer, and in this case a very specific 2-photon photoinitiator. And with that, you can, for example, use a gelatin-based material. So you can, with hydrogels, you can get quite high resolution. We once printed the National Monument of Belgium, so the Atomium, which is a very impressive structure, using gelatin. But you can also do this for cell culture. So in this case, we seeded some cells on a microscaffold of 300 micrometers, and we saw that after 7 days, cells completely take over the shape. Of course, you can do even more impressive. We printed once the Brandenburg Gate, for example. You can have scaffold structures, or even in this case, these are corneal endothelial cells which are oriented on top of 3D printed gelatin ink. Also do it with living cells inside, and you can use it for other applications. So for example, again, in the lab of Alexander Ovsyannikov at the University of Vienna, they use this technology to make cages for spheroids to get an injectable structure. So in this case, they print these tiny cages, put spheroids inside. Why do they want to do this? because if you have normal spheroids and you put them in culture together, they will fuse, they will form a necrotic core, and they will shrink again. If you put your spheroids inside these cages, you can inject them, they will fuse, but they will not shrink because they're precluded from it. And in between these different cages, there's still enough space for nutrients and waste to transfer. You can see here that in 24 hours, your cells take up the shape of your 3D printed structure. And with this, you can actually do stuff which is against nature in a way. You can have cubic or pyramidal spheroids should you want to. And the idea is that over time, the material breaks down and your tissue forms. They even managed to print thousands of them and actually fill some cracks in defects. So you can see here a whole cluster of these spheroids with cartilage cells. By now, they also made a new bioprinter, which is a lot faster. So this is real time. This is not accelerated anymore, where they can 3D print these cages 12,000 per hour, basically. Now they also did some in vivo tests, which were very promising with this technology. I see that there's a picture missing, so I'll skip this. So what you can also use this technology for is this organ-on-chip application, because the benefit of two-photon polymerization is you can print directly inside a microfluidic chip, where you can influence cells down to the single cell level if it be needed. For example, here we printed a 3-channel approach in which we always printed a microscaffold with breast cancer cells to have a tumor model on chip, basically. We use this for other applications, so placental barrier model, osteosarcoma drug screening, blood vessels. So the technology is so precise that you can even make a microvasculature. So we managed to have lined blood vessels down to 10 micrometers diameter. You can also use it for tissue models. So in this case, they used a cancer spheroid, printed a dome on top of it in one of our gelatin-based resins to then study the effect of cell migration, of cancer cell migration. And even further here, this is also a model for cancer metastasis, where they have this cancer niche. This is a blood vessel, and then they see how the cancer cells migrate from the cancer niche into the blood vessel, and then would move around the body to better understand how cancer cells are spreading throughout your body. Also a bit spectacular, you can use this for organ on chip. So we are currently in a project, Astrocardia, where we're actually studying heart aging. It's a project of 5 Flemish companies, where we want to 3D print a microscopic heart model on a chip, which will be sent next year to the International Space Station to study the influence of aging. You can mimic a lot on Earth, but aging is very difficult. And for that, we're printing in high resolution these cardiac cells. We incorporate a vascular bed to feed them. And of course, we want to print directly into microfluidic chips. The technology we use for that is two-photon polymerization. And if you want to learn more, we published a review on two-photon polymerization for biomedical applications in 2023 in Advanced Functional Materials, which I would invite you to read if you're interested in. So here we printed this heart cells, and the nice thing about these heart cells is that they beat actually. And around this, we printed this microvascular structure, which is then, this is in the chip, which is then put in a carrier module, which we then plugged into the International Space Station next year. So basically here you can live see the printing process. You can see the laser moving. This is a spheroid of cardiomyocytes, and you can see this, the blood vessels being printed around it. And as a result, you get a beating heart, but it's not beating for some reason. Doesn't matter. That's two-photon polymerization or multi-photon lithography. So then the next technology, light-based, is digital light processing, which is technically the oldest 3D printing technology in the world, because it's derived from stereolithography, which was originally patented in the 80s by Scott Hull, the founder of 3D Systems. So if we look again at processing, what's important here? video is not working. So basically how this technology works is you have light source, then you have a digital micromirror device, which is an array of all small mirrors. Every mirror is 1 pixel, and you basically shine your light to a container of resin. Everywhere that the resin is irradiated, it will solidify, it will cure, and everywhere where it's not, it will stay liquid. And this is how you can print something in a layer by layer fashion. So you print 1 layer, then you move your build platform upwards, you irradiate the next layer, and that's how you get 3D printed construct. What's important here from the BIO ink, your material needs to be photocross linkable. In this case, it needs to be liquid because your print bed moves inside of it. And what's crucial here is that the light should have a low penetration depth, because as I showed before, in conventional single photon processes, you would have a reaction everywhere along your beam path because every photon has the required energy to induce the reaction. So therefore, it's important that you limit your penetration depth, otherwise your resolution in the Z direction would be completely lost. And this you can do by playing around with the formulation. So again, the basis of your resin, of your bio ink, is a photopolymer and a photoinitiator. In this case, you also add a photoabsorber. And this is a component, typically a dye, which absorbs excessive light and then converts it into fluorescence without inducing any reaction. And for example, there was a publication of Professor Koen Lim back in 2018 using hydrogels for photon polymerization. I don't know why the images are not showing. Anyway, so they showed the difference when you include a photo blocker or not. Well, basically you lose all the resolution. So basically you see here what happens if you don't have a photo blocker. So even with a simple structure like a cube, you get a very blob after printing because you have a lensing effect of your printed structure. And if you include a photo absorber, you can get this nice structures which translate into very, very fine features. So with this, you can print actually quite some complicated structures. For example, here you see a gyroid scaffold with some cells on top of it. And the nice thing about this picture, this SEM picture, is you can see the individual pixels of your digital micromirror device. Again, you can use shape memory behavior here. So you can print a complicated shape. And then if you have a polymer with shape memory properties, if you heat it up, you can deform it. If you then cool it below body temperature, it stays in this temporary shape. And if you then put it in body temperature, it will go back to its complicated 3D printed shape. Something you can also use for minimally invasive applications. You can use gelatin-based material. And then the last printing technology is volumetric bioprinting. So this is the most recent bioprinting and 3D printing technology. And this is actually very, very spectacular. Also first published in the lab of Ricardo Levato in Utrecht. You can see here how it happens. This is real-time printing. So in this case, you have a rotating resin container where you basically have your structure in, and it's a reverse CT scan basically. And all of a sudden your structure appears, and this is real time. So it only takes a few seconds regardless of the size of your construct, which is indicated here. For example, if you compare it to extrusion-based printing, if you have one structure at scale 1, 2, or 3, in extrusion-based printing, it goes super fast. It increases the printing time a lot. In digital light projection, it only increases, it's only dependent on the Z direction, so on the height of your structure. But with volumetric printing, it always takes the same amount of time, which in this case is 22.7 seconds. Here on the formulation, you again have a photopolymer, a photoinitiator, and something which is added sometimes is a radical scavenger to increase the resolution. And with that, you can actually get a structure. This was, for example, something we did in our lab a few months ago for Pi Day. We printed this Pi letter in a gelatin-based resin. And as you can see, this is real time. It's about 30 seconds, I think. You can already see it appearing. Afterwards, you just dissolve the material. and you get your structure. The benefit of it being so fast and using blue light is it has exceptional biocompatibility. So there's almost no dead cells after printing. And since it's so fast, this opens up the dream that one day you could have a bioprinter inside the operating theater where you could harvest your cells, 3D print your structure and put it back in. But for that, of course, you need biocompatible materials, for which we are collaborating with Ruggelo, the biggest gelatin supplier in the world, with whom we launched last year GMP-like material, very first GMP-like material. So if you want to go into the BioINX field yourself, we have compatible materials for all printing technologies, which are plug and print, which is important to translate this technology from the research into the clinics. And with that, I want to conclude my talk, hoping that I could convince you that biofabrication is a very promising technology and that there's been tremendous technological advancements, that there's still a long way ahead towards really printed organs, but we're setting the first steps, and there's very high near future potential in drug screening. But I hope you also understood that the materials are key there. And before I end my presentation, I would like to advertise a conference that my co-founder, Sandra from Ghent University, is organizing next year in Belgium. So it's the biggest European conference on biomaterials. So I'd welcome you all in Antwerp. And with that, I would like to thank you for your attention, and we can go to the questions.
Thank you very much, Jasper. That was a very exciting talk, despite